Hello everyone and welcome back to another video. Today I wanted to go over the replication crisis, explain some of its causes, some of the statistics behind it, and some potential proposed solutions, and how it should affect our overall view of science. So, in 2005, John Ioannidis published an article titled "Why Most Published Research Findings Are False." And in this article, he points out that the methodologies and study structures used in modern science have led to a high rate of non-replication in published studies, and as a result, he argues that it can be proven that most claimed research findings are false. And this conclusion isn't only limited to this paper. Later research has also verified his findings. So one study or one survey that surveyed different scientists found that more than 70% of researchers have tried and failed to reproduce another scientist's experiments, and more than half have failed to reproduce their own experiments. Along with this, they found that 52% of the scientists surveyed, or the researchers surveyed, said that there is a significant reproducibility crisis. And it's not like the other 48% said there is no crisis. 52% said there's a significant crisis, 38% said it's a slight crisis, and only 3% said there's no crisis. So most scientists seem to agree that there is this reproducibility crisis or replication crisis in science. And this crisis extends across fields, but it is particularly bad in certain fields. For example, we can look at psychology and cancer biology, which found replication rates of 40%, around 40% and around 10% respectively. Additionally, in medicine, of the people surveyed, the prediction range people tended to think that only around 50% of studies could be replicated in their field. Now, some fields it's less of a concern. Physics and engineering, less of a concern. Most people believe that most of their studies are reproducible. That makes sense because most of these types of studies in physics and engineering, there's less of a hypothesis testing sort of orientation to those studies, while like medicine, psychology, it's a lot more focused on hypothesis testing, which we're going to get into later in the video. But this crisis does extend across fields. There's some famous examples in physics of studies that were published that proved to be difficult to replicate later on, and we'll get into those examples soon. But before we do that, let's look at some studies in psychology. So in psychology, they looked at 100 psychology experiments, and they found that there are statistically significant results that were reported in 97% of the original studies. But upon attempting to replicate, statistical significance was achieved in only 36% of the replicated studies. So that's psychology. Really low replication rate. Next, there's a study that looks into these highly cited clinical research studies. There's 49 highly cited clinical research studies, and 45% of them, or 45 of them, claimed that intervention was effective. So a lot of them claimed that there was an effective intervention. Of these, 7 of them were directly contradicted by subsequent replication studies. 7 others found effects that were found that the original studies had effects that were stronger than those of the subsequent studies. So basically, the replication studies show that the effects of the intervention weren't as strong as was shown in the original studies. And then 20 of them were replicated, which is good, but that's only 44% of them that were able to be replicated. And then 11 of them remain largely unchallenged. So either they weren't able to replicate them, they weren't able to directly replicate them, but they didn't directly contradict or show effects that weren't as strong. So in this case, only 44% of these clinical research studies were replicated, which is an extremely low rate. So with all of this, let's go into a few examples, because these are just broad studies, broad overviews of these different studies. But let's jump into a few examples. So one famous example is the marshmallow study. And this study is kind of a test on delayed gratification in children and seeing how it pans out later on in life. And basically the way the study worked, They gave 4 and 5-year-olds, they said, you can have this treat now, which is a marshmallow, or you can have 2 when they come back. So they leave the marshmallow in front of them and see if they can delay gratification and wait for the second one when they come back in the room. And what the study found is that the kids who couldn't hold out long, they generally grew throughout their teens, their 20s and 30s, quicker to frustrate, weaker in academic and social skills, and with more drug use, mental health, and weight issues. And all of this was like a well-publicized, or this was a published, very like well-publicized research study that was very popular at the time. But since then, people have struggled to replicate these studies. So someone attempted to follow up on the study, and it finds that kids who quickly gave into their marshmallow temptation are generally no more or less financially secure, educated, or physically healthy than their more patient peers. So that's one example of a famous study that was difficult to replicate. And then additionally, there's this article that has 10 famous psychology findings that have been difficult to replicate. One famous one is power posing. I saw this in like a crash course video on the replication crisis. I think this must have been a big thing back when I was 9 years old. So a long time ago. It was like famous TED Talk, I think, Your Body Language Shapes Who You Are, basically saying if you power pose that you're going to feel bolder and you're going to be more successful and stuff like that. And this was a published paper cited over 450 times, but difficult to replicate. Another one is smiling will make you feel happier. This is probably one that you've heard, smiling making people feel happier, but replication attempts found that there's no effective mouth position on the funniness of cartoons in this particular example, which I think was the thing that they were studying from before. Then another one, self-control is a limited resource, and then there's a bunch of other different examples of studies here. So, next we have some examples in physics. So, as we saw before, in physics, there was generally people were the most confident in the reproducibility of their published results, and because of that confidence, they were also the least likely to take concrete steps to improve reproducibility. So physics in general, it's less reliant on hypothesis testing, less reliant on the statistical tests. So it seems like reproducibility would not be as much of an issue. But this article, which I'll post in the comments below, is going to have different examples of different cases of places where physicists have published studies and these studies have been failed to replicate. Another example is in physics is the finding that a neutrino traveled faster than the speed of light that got published, and ultimately people were not able to replicate this, but the study still got published, and there were certain errors that they found later on in the way that they were measuring the speed of the neutrino. But this study did get published in 2011. Another example is cold fusion, where these two electrochemists found that you could produce a nuclear reaction at a colder temperature near room temperature. And scientists failed to replicate this experiment later, but this was something that was published originally in physics. So there are examples in physics, but they're a lot less common, and they tend to be a lot more quickly refuted than other sciences as well. So with all of this, I think to understand more about why this replication crisis is occurring, I feel like it is useful to go into some of these statistical methods that are being used by these studies to understand sort of why things are going wrong, where things are going wrong, what's actually going on with this replication crisis. And to understand this, I think we need to talk a little bit about hypothesis testing. And basically, modern studies use hypothesis testing in order to establish significance of results using these values called p-values. And one study found that hypothesis testing was explicitly used in 79% of studies that they looked at in this particular study. And in here you see this acronym NHST. Earlier in the paper they say that that's null hypothesis significance testing, which is hypothesis testing that I'm going to explain in this video. So with that in mind, knowing how prevalent this type of testing is, let's go over the basics of how it works. So to begin with, we have our null hypothesis, which we're going to denote, which is often denoted as HO. This is considered the null hypothesis, and it represents our baseline assumption. It indicates results that are not statistically significant in these studies, and it's our baseline assumption, basically. In contrast, we have what's called the alternative hypothesis, which is HA. This is how it's often denoted. Sometimes you'll see like a H1 as well, but we'll focus on HA in this video, or we'll use HA in this video. And this is the claim that the study is trying to test. So for example, let's consider like a drug's effectiveness. The null hypothesis would be the drug is not effective. And the alternative hypothesis would be the drug is effective. Okay, so then once we establish our null and alternative hypothesis, we perform a study and we collect data. And with our data, we calculate what's called a p-value. And the p-value represents the probability that we see the observed data or a more extreme result, so the observed data from the study or something more extreme in the direction of the alternative hypothesis, given that the null hypothesis is true. So given the null hypothesis is true, whatever the distribution we'd expect with that, what's the probability that we see the observed data or something more extreme in the direction of the alternative hypothesis? So let's continue with this drug example. For this example, let's assume that we have a cholesterol reduction drug. So in this case, the drug is effective if it lowers cholesterol. So in the case of the null hypothesis, that would mean cholesterol reduction equals 0. We'll use CR to represent cholesterol reduction. And then for the drug being effective, cholesterol reduction would have to be greater than 0. It reduces the cholesterol. So cholesterol reduction is greater than 0. Now, even if the drug doesn't reduce cholesterol, the person's cholesterol levels will still likely fluctuate. So if the null hypothesis holds, we could still expect to see the person's cholesterol levels varying just according to some probability distribution. So let's assume that the cholesterol reduction that we would expect if the drug is ineffective, so just assuming that you gave them a sugar pill, it was a placebo, the amount of cholesterol reduction falls within some probability distribution. Because, I mean, our body's cholesterol levels are changing all the time, things are constantly happening, so we could assume that this is the probability axis here. And then this is cholesterol reduction. And then I will try to draw a bell curve. Not always great at drawing these. Okay, I think that's okay. That's good enough. But we'll say, so the cholesterol reduction level is going to fall somewhere between 0 and some of these n's. But in general, if the drug's not effective, we'd expect the probability of the cholesterol reduction, it's going to be clumped around 0. So this direction would mean reduction, the cholesterol is going down. This would mean cholesterol increase. pretty equally likely either direction. But it's possible that we could see a significant cholesterol reduction even if the drug is not effective just by regular fluctuations, like maybe you ate something different that day or didn't eat that day, so your cholesterol goes down. Or on the other hand, you eat like a massive fatty burrito right before you get tested, so your cholesterol spikes up right beforehand. Something like that. Now, suppose that we have an observed cholesterol reduction from the study that we perform. So this is the observed reduction. Or we'll just say it's the observed data. Now what the p-value would be in this case is the p-value corresponds to this probability here. So in this case, the p-value represents a shaded region. It's the probability of obtaining the observed cholesterol reduction or a higher reduction if the null hypothesis is true. So we're on the null hypothesis's probability curve. We're assuming the null hypothesis is true. And then we have the observed data, and we think, what is the probability that this or a more extreme effectiveness or a more extreme cholesterol reduction would occur if we assume that the drug is not effective? Now, low p-values mean that it's less likely that the null hypothesis is true. So we say that we would reject the null hypothesis if the p-value is below a certain threshold. If the p-value is low enough, it's less likely that the null hypothesis is true. So say we have this absurdly low, like high cholesterol reduction after taking this drug. It's not very likely in that case that the drug is not effective. We have some evidence that the drug is effective in that case, because the p-value becomes extremely low as a result of this, or the p-value is really low as a result, or when you calculate it for this observed data. However, on the other hand, say you have observed data of a cholesterol increase, so a negative cholesterol reduction, then you shade this entire part of the curve. The p-value is huge. Like, say over here it'd be maybe close to like 80%. So there's like, it's very unlikely that, well, you wouldn't be able to reject the null hypothesis in that case. Now, typically, the threshold that researchers choose, and this threshold is referred to as the significance level, which is alpha, and typically that's how it's denoted. Typically it was with alpha. Typically researchers choose alpha equals to 0.05. So what this means is a p-value so you reject the null hypothesis if p-value is less than 0.05 and fail to reject the null hypothesis if p-value is above 0.05. So in the case of our cholesterol reduction drug, if the observed reduction or higher than that reduction would only occur 5% of the time or less if the drug was ineffective or the null was true, we would conclude that we reject the null because the p-value in that case would be below 0.05. Otherwise, if the p-value is greater than 0.5, we say fail to reject the null. We have no evidence that the cholesterol drug is effective in that case, so we fail to reject the null. Now, we typically say fail to reject the null in this case because we're not providing evidence of the null hypothesis being true. That's a more nuanced statistical discussion, which I won't get into super specifically in this particular video. But okay, so with all of that, I think while this method seems effective at first glance, what it also means is that in a perfect world where scientists make no mistakes, have no biases, ineffective drugs are still going to produce studies showing that they are effective 5% of the time. Because in the case of an ineffective drug, in 5% of these studies, you're going to have an observed data that passes this 5% threshold just by chance. So we would say that they're effective in that study. So in other words, if we perform a study on 1,000 ineffective treatments, we'd still expect to have scientific evidence for the effectiveness of 50 of these different useless treatments, just because 5% of the time, assuming a perfect world, which we don't have, as we're going to get into later in this video, assuming this perfect, unbiased scientific world, we would still have 5% of these studies showing effectiveness where there is none. False positives, type 1 error, showing false positives, basically. And I think this is why replication is so crucial. Assuming that we can produce two independent, identical studies of the same drug, the probability of a null hypothesis being incorrectly rejected and finding evidence of effectiveness for the ineffective drug drops to 0.0025 or 0.25%, which is significantly better than this 5% issue that we were talking about here. Okay, so with all of this, if you find these statistical concepts to be a bit confusing, don't worry, you are not alone. These are complicated concepts, and it's like the specific language that you use can be very important, like whether you say fail to reject the null or have evidence to accept the null. That's not, like, you can't have evidence to accept the null in a statistical study. But now, if you find all of these statistical concepts a little bit confusing, don't worry, you are not alone at all. I think even the researchers performing these studies don't understand p-values. They don't understand how p-values work. For example, in a study of medical residents, they found that while 88% of these medical residents expressed fair to complete confidence in understanding p-values, only 58.8% of the residents chose the correct answer for how to interpret a p-value later on in the survey. So let's look at the question that was asked of them and see if we can get the correct answer from this. So it used a multiple choice format with 4 potential answers for the correct interpretation of a p-value greater than 0.05. So this would basically mean, in this context, if the null hypothesis is true, if the p-value is greater than 0.05%, that means that the observed data or something more extreme would happen in greater than 5% of instances, or greater than 5% of the time, assuming the drug is not effective. So this would, if we assume that this alpha of 0.05, this would mean that we'd fail to reject because the p-value is greater than 0.05. We could explain this pretty easily. It's just assuming that the null hypothesis is true, basically. Yeah, it's not inconsistent with the null hypothesis being true because the observed data or something more extreme would happen in greater than 5% of instances anyways. So let's look at the answers here. A, the chances are greater than 1 in 20 that a difference would be found again if the study were repeated. B, the probability is less than 1 in 20 that a difference this large could occur by chance alone, or is less than 1 in 20 that a difference this large could occur by chance alone. C is the probability is greater than 1 in 20 that a difference this large could occur by chance alone. And D is the chance is 95% that the study is correct. So A and D, I think, are obviously misleading because none of these are really what a p-value is testing. The chances are greater than 1 in 20 that a difference would be found again if the study were repeated. No, because you'd have to know if the study were repeated, it would mean that it's repeated with the actual distribution, not this assumed null distribution. So this has nothing to do with the p-values. Probability is less than 1 in 20 probability is greater than 1 in 20. These two are closer. The problem here with both of these is they're not, they say by chance alone when they should be saying conditional if you assume that the null hypothesis is true, then the probability is greater than 1 in 20 that a difference that large could occur. So the by chance alone is a bit misleading. The chance is 95% that the study is correct. That's not what a hypothesis test is testing either. The best answer here is C, but ironically, even C isn't fully correct here. It's the best answer. So the fact that 58.8% still got this wrong is not great. But additionally, the fact that none of these answers are really demonstrate a correct understanding of how p-values work, that fact is a little bit disappointing, and it indicates a widespread prevalence, and even beyond what the study was trying to show, that these medical residents didn't understand p-values. The researchers who wrote this study from this question alone don't appear to understand p-values either. And this article particularly points that out as well. In fact, none of the 4 choices are correct. So not only the residents who picked choice C wrong were the residents who picked choice C wrong, but also the authors as well. Additionally, this paper was peer-reviewed and published in a prestigious medical journal, which is crazy. Like, the fact that they could let such imprecise and such honestly misleading language about p-values just slip through, it indicates that there's this widespread misunderstanding and misuse of p-values. Like, this study was peer-reviewed. Nobody caught this. It seems that people don't have this in-depth understanding of p-values, and they're statistically complicated concepts, but this is like the entirety of what the studies that they're creating rely upon. And it's not just me pointing this out. This misinterpretation of p-values has gotten so bad that the American Statistical Association decided that they had to publish a statement on p-values just to explain their proper interpretation and how to understand what p-values are, because there is widespread misinterpretation of it. And this was published in 2016. Additionally, along with this, there is evidence for a practice called p-hacking. And p-hacking basically occurs when a scientist performs tests or gathers observations until the tests give a statistically significant p-value. And if this practice were prevalent, we would expect to see a spike in test results that is just below that 5%, that 0.05 threshold, that alpha value of 0.05. So those p-values would be clustered right before that 0.05, just enough to be statistically significant. And lo and behold, that's what we see. We see this little spike. In general, we should expect this frequency to kind of decrease over time, but there is this little spike here at the end, and this study claims that this p-curve shows evidence for evidential value in p-hacking, a rise in p-values just below 0.05. And this is an unethical study practice. This is completely unethical. They should not be continuing the study until they can get a p-value that's significant. That's extremely misleading and just not a good practice in studying. So this is not like something that we should consider as something that's okay. Oh, that's fine. People p-hack. Yeah, that's fine. Whatever. Who cares? No, this is something that is very like unethical and misleading when it comes to scientific studies. But okay. So, with all of this in mind, why does the replication crisis occur at the rates it does? Obviously, we've talked about p-hacking, we've talked about misunderstanding of p-values, we've talked about how inherently there will be like this 5% rate of false positives if we just based on the alpha value, the significance value that we're choosing. But with all this in mind, why does it occur at the rates that it does? If you remember before, the psychology studies, Statistical significance was only achieved in 36% of the replicated studies, which indicates this false positive rate of at most it would be like 64%. It might be slightly lower than that because maybe the replicated studies are slightly wrong, so there's issues with that. So at most, like 64%. It's a lot higher than 5%. We'll say that. And then in the medical example, where it was 16% of them that were literally contradicted by these subsequent studies, and only 44% directly replicated. Like, these are higher than these 5% thresholds than this like inherent 5% false positive rate that we see already. So what's causing us to see an even higher rate of statistically significant studies that are impossible to replicate? And the main cause of this crisis, if you look into this a little bit more, is a publication bias that favors new and significant results. To advance in the world of science, you need to get published, and studies with new and significant results are way more likely to be published. There's not as much incentive to spend a lot of time just trying to reproduce the work of your peers, when you could be spending time researching something new and exciting, something significant, something that's going to get a lot of press, something that'll get you a TED Talk on power posing. And additionally, papers that fail to reject the null hypothesis are less likely to get published for the same reasons. People want to see something significant. People want to publish studies where there's some new significant trend being discovered or some new significant treatment being discovered. People are not as likely to publish something disproving a treatment being true, showing that, oh, there's no evidence to reject the null. There's no evidence to reject the fact that this treatment's ineffective. Additionally, the competitive environment in scientific funding, career advancement, patents, all this stuff, makes researchers a lot less likely to fully report their data and methodology, which hurts transparency, and transparency is necessary for replicability, because if you don't have everything that the person did to create the study in the first place, it makes it impossible to replicate because you don't even know how to replicate it. And I think all of these issues taken together, like beginning with the fact that 5% false positive rate that we'll already see just because of the alpha value, and given the p-hacking that we've already talked about, given the misunderstanding of p-values, given this desire to make significant results, I think all of this together explains why there are so many significant and non-replicatable studies out being published. So, with all of this in mind, let's go over a few proposed solutions. Now, first, I think the most obvious solution to this is more incentive for replication studies. As obvious as that sounds, there's more funding for replication studies, more incentive for them, a scientific culture that is more focused on trying to replicate studies rather than finding new significant results that'll get you a lot of press. And I think if the scientific community values replication more, it can improve the credibility of its results and help fight back against this significance bias that pervades the scientific community, this publication bias, this desire to produce significant results. I think another solution would be the publication of more null-affirming studies. If researchers don't have to reject the null to get published, there will be less incentive to p-hack or to perform other unethical study practices to try to make the results significant so that they can get published. Like, at the end of the day, these people want to get published. Like, that's so much of what it is to be a scientist, so much of what it is to advance in the scientific career is getting published. And if you can't get your results to be significant, there's so much just professional incentive, so much financial incentive to just make those results significant. Just do a little p-hacking. So with all of that, I think, and then next, I think another crucial solution to this would be a better education on how p-values work. And I think this will help us just increase scientific literacy. If we educate more people on how p-values work, like in the broader culture, in the scientific fields, people we'll see a general increase in scientific literacy, how we read these studies, how we interpret these studies, how we act based on these studies. One study alone doesn't mean very much, and it would benefit our scientific understanding significantly if we held that belief more intuitively. And then finally, another proposal is that we reconsider this p-value cutoff of 0.05, as it may produce, like the current p-value cutoff, the significance cutoff of 0.05, may produce more type 1 error or more false positives than we're comfortable with. And given that the widespread acceptance of alpha equals 0.05 is arbitrary, we should change it if the results that we're seeing aren't optimal, if we're seeing a lot of significant studies that are difficult to replicate. So the idea would be lowering it to make it more difficult to produce significant studies. And obviously there's different trade-offs like that. Like that would hinder the ability to produce true positives too. We'd be rejecting more positives. We'd see more false negatives as a result. But if we have a huge problem with false positives right now, it would make more sense to reduce alpha down to 0.005 or 0.01 or something like that, something lower than 0.05. But these are just different proposed solutions that I've seen, and I think each of them has their own potential benefits, potential drawbacks, but yeah. And next, with all of this in mind, let's take a step back and analyze what this should mean for our overall view of science. I don't think that the replication crisis discredits science as a whole. Science is still a very powerful tool that we have to interface with and understand the world. But I think we have to understand that it's just that. It's a tool that we've created and that we use to understand the world. And I think that as a result, we need to be careful to not just accept scientific claims uncritically, and instead always try to question the methodologies and assumptions that we're using, as well as our own biases that may make us more excited to accept some scientific results than others. And I'd also like to encourage a lot more introspection and transparency about our biases while interacting with science and other truth claims, as well as a reassessment of our confidence levels in the claims of science. While science tends to self-correct over time, or science tends to self-correct over time, but it's not done self-correcting yet. It's a process of human knowledge that we're currently in the middle of, and it is filled to the brim with human bias and short-sightedness and desires for professional gain, all that sort of stuff. So I think science is great, and I don't want to discredit science as such, but I do think that this should adjust our view of science rather than treating it as this thing that gives us truth. This thing that gives us truth that we can accept uncritically. I think we need to critically analyze our assumptions, our biases, and consider what we're excited about accepting from science versus not accepting, and just adjust our confidence levels accordingly. Okay, and with all of that, let's open it up to the comment section. If I made any mistakes in this video or you disagree with anything that I've said, please feel free to call me out in the comment section below. Additionally, if you enjoyed the comment, please feel free to like and subscribe. And if you're feeling very generous today, please donate to my Patreon, and the link for that will be in the description. Additionally, I have a Discord. It's very, very, very dead right now. There's no one posting in it, but it would be nice if it was a little bit more active. It would be fun to talk to people if people have questions, to be able to talk in there. I think would be more interesting, a more like one-on-one setting rather than trying to chat in these YouTube comment sections that can very quickly get out of hand. But yeah, so I'd like it to be more active. The link to that is also in the description. Let me know if that link works. I hope it still works. I set it to be indefinite, but hopefully it still works. And then additionally, all of the studies that I went over here are linked below. I didn't explain things super in depth, obviously, so if you are more interested in any of these topics, like go read through each of those, go learn more stuff. I try to do kind of a high-level overview of everything. which obviously comes at the cost of not getting as in-depth as I would probably like to in each of these different topics. But with all of that said, thank you all for watching, and I hope to see you all in the next video. Peace.